All right, so without further ado, our next lecture is going to be on transformers theory. And to present that, I'd like to invite Ryan Chi. Ryan, take it away.
Thanks, Pranav, for the welcome. Hey, everyone. Thanks for coming today to listen to this lecture on transformer theory. Really excited to be here. As Pranav mentioned, my name is Ryan, and I'm really happy to be taking you through this lecture on the theory and the fundamentals behind transformers. Without further ado, let's get started. So Pranav, is the sort of the norm that we all share screen? All right. Can you see my screen? Awesome. So as I mentioned, I will be talking about the theory behind transformers. What are the learning outcomes of this section? The learning outcomes are, after this lecture, you will be able to obtain a comprehensive understanding of the fundamental theory behind transformers. Some of the things that you will learn are attention, embeddings, and tokenization. If you already knew these concepts, hopefully you'll have a more concrete and finer-grained understanding after this lecture. In addition, we are hoping that you can understand the difference between MLMs and LMs, as well as familiarizing yourself at a Jupyter Notebook level with each. Hopefully this should help you as you listen to and work on the concepts from future lectures. Let's start by motivating the fundamentals of attention. So deep learning methods have achieved success on data with constant dimensionality. Maybe to think of this concept, think of tabular Kaggle style data with a constant number of features, or an image which has constant size and can be processed with a constant number of CNN layers. Each one, will make the image either smaller or larger, and this is all deterministic. But the problem starts once you try to deal with data of unbounded size. For instance, text can be of arbitrarily length. It can be arbitrarily long or short, and we might want to define operations that both process sequences of unbounded length and generate sequences of unbounded length. After all, this is what we do, as humans when we understand and generate speech. The traditional option is to use a recurrent model, which performs one operation over each element in the input. However, optimizing these kinds of models can be tricky. As it turns out, propagating across numerous time steps ends up being pretty hard to optimize. Think of problems like the vanishing gradient. There are, of course, ways to work around this, but like pyramid models that combine information at different levels of granularity. But in general, this problem is unsolved. As you can see, up here I have an illustration of an RNN model, but this is hard. It's worth noting that models like LSTMs, which are designed to model both short-term and long-term dependencies, were designed specifically to deal with. But again, this was still not solved, even after developing this new architecture. LSTMs are still notoriously tricky to train, and there still is that problem present in these models. The standard approach, as I'm alluding to right now, and I also have outlined in the new paradigm section, is to use attentional models. These models are able to draw info from any point in the sequence. They do so by using the attention mechanism, which dynamically combines information from all points using a single vector, using a weighted sum. When this process is iterated, it allows deep models to gain extremely fine-grained information about how different tokens in the input can relate to each other. Although attention can be used in other models, it has most famously been used in transformer models such as encoder-decoder transformers, BERT, and GPT, as well as its derivatives. More on those later. We'll start by quickly motivating the math behind attention, and hopefully this can give you a better feel for what it really does. There are obviously formal descriptions of attention available online, but the quick summary is that the attention operation entails taking a weighted sum of all elements in the sequence. To compute the sum weights, one typically compares a dot product in a projected space between the element that we're trying to compute information from, which is referred to as a query, and the set of elements that we might be trying to draw information from, called the keys. By projecting these queries and keys multiple times into multiple learned subspaces, this is called multi-head attention, our model can pick up on different attributes of the vector space and use that to perform fine-grained operations. And yeah, as I said, this process is called multi-head attention, and it gives you a lot more flexibility than the single head attention that was previously used. Now, let's move on to talking about the two major kinds of attention operations. They're outlined in these two boxes on this slide. These are famously used in the transformer developed by Vaswani et al., but you can use them in arbitrary parts of a deep learning model to integrate or process any kind of vector-valued sequence. In particular, let's talk about the difference between self-attention and cross-attention. Self-attention is when the similarity is taken with respect to all elements in the same sequence. To be precise, given a sequence of elements x1 through xn, we compute an updated vector for xi by computing its projected dot product similarity with all vectors in the sequence, and that includes itself. Typically, one then feeds the attention-derived vectors through the MLP linear layers to produce a final set of vectors. By repeating this process multiple times, you get contextual representations, where each vector has information not only about its original vector value, but about all other values in the sequence. This is a major advantage of the transformer compared to attention models compared to previous approaches, as we'll discuss in a little bit. As you might imagine, this kind of approach is extremely good for building good sequence representations in both NLP and vision. Cross-attention, on the other hand, is when you compute the updated embedding x sub I by attending to a separate sequence of vectors v1 through vn. This allows you to contextualize vectors not just based on the current sequence, the x tokens, but also on some other sequence that you want to condition your model on. Cross-attention, therefore, is really great for combining information from multiple sources. It's particularly popular for sequence-to-sequence tasks such as machine translation or image caption. You can think of like two different cases where cross-attention is applied when the two sequences are of the same modality, such as translation, right? You might, attend to, if you're translating from English to French, maybe you're attending to one sequence, which is in English, and you're also simultaneously attending to the other sequence in French. But the point remains that they are in the same modality. It's just helpful because you can better model the relationship between words by attending to these two sequences of the same modality simultaneously. This is also true when you have two different modalities at play, say vision and text. In this case, because these are two different modalities, a different encoder model is usually required, which the output generator then attends to. Okay, I think we spent a decent amount of time on attention. So let's turn our attention. Let's start to turn our focus to embeddings, which are another key part of transformers. In this section, we will go over embeddings. So why do we need, what are sort of the considerations and the concerns that we have when we talk about embeddings? Well, to give some context, most machine learning models by design take in and produce continuous representations. For example, an image naturally takes on vector values between 0 and 255, think RGB values, while an audio sequence consists of a series of audio levels at each time. Since our models are continuous and differentiable, this makes them easily optimizable, which is what we need. However, this is not such an easy situation for NLP, since words are inherently discrete. There is no such thing as a continuous variation between words, as we only have so many letters in the alphabet and so much space in the dictionary. So the question is, how might we solve this? And maybe you can take, a few moments to think by yourself. We probably won't take the whole minute, but maybe you can think about this so that, you can give this possible solution some thought before we give the answer. All right, hopefully you gave that some thought. So the standard NLP solution is to represent each word as a vector, which takes care of this issue. This is a good idea. However, how are you going to implement this? Maybe one easy method, and this has been used before, is to use one-hot vectors, which consists of a matrix where each row only has one, and the rest are zeros. To do so, number each word 1 through n. Computing a vector for a word indexed I then involves just producing the unit vector with a 1 at index I. This approach does work. However, since there is no explicit relationship of what these words actually mean, it can be difficult to generalize to new words. And another drawback is that there's no inherent relationship between words that really should be related. For instance, you might imagine that it would be nice and also probably pretty helpful for the model's understanding of language if the vectors for king and queen were at least somewhat similar, because these are highly similar words. But unfortunately, in this easy method, these two vectors are orthogonal, and they're also not entirely related because they're merely just two one-hot vectors. They're about as related as any two random words, which is obviously not ideal. Another method that perhaps is more linguistically motivated is to add linguistic features, such as, say, part of speech or semantic meaning to these vectors. One might imagine that we will use POS tags or WordNet semantic relations to inform our design decisions there. However, these concepts are pretty not flexible, and it turns out these approaches end up being pretty rigid and hard to implement. So we talked about what might not work. What does work then? The breakthrough method in NLP research was the introduction of self-supervised methods, where the meaning of words is automatically ascertained from their context. To be more clear, these take advantage of distributional semantics, which, put in maybe layman's terms, is the fact that words' meanings can be determined from the context in which they lie. That is, the words that they co-occur with. How might we do this? Well, we might embed each word using a co-occurrence matrix. That is, keep track of how many times word X appears within the context of word Y. This then creates a vector space that allows for vector arithmetic. NLP researchers and maybe the broader science community were not only shocked, but also very excited when it turned out we could do vector arithmetic in this space. For instance, if we added the vector for king and subtracted the vector for man and added the vector for woman, we would actually get the vector for queen. which is as every student who's done their proper share of word analogy problems knows is the correct answer. Or we might say we can add, take Brazil and subtract Brasilia and add France to get Paris. Therefore, the standard approach these days is to start with a word embedding and, I missed one part. Maybe one drawback is that instead of getting specific context, what's really going on here is that the embedding for each word is just taken to be the average of all its contexts, weighted by how often they appear. You might think of, in linguistics, we call this polysemy, where a word can mean different things. For instance, scale can refer to maybe something that measures things, and also like a musical range. And what it means in any particular situation is not entirely clear to this word embedding method. Instead, it's just taking the weighted average of all these different meanings. So this is definitely a con. What does solve this is transformer models, which are context sensitive. And so this is the standard approach these days is to start with a word embedding and then plug that into contextualized models like transformer encoders that we've discussed and will continue to discuss. Okay, so we've now gone up to both attention and embeddings. Let's focus on something else, specifically tokenization. But before that, maybe we can talk about what's going on in embeddings revision. Pre-transformers, the paradigm was to use these really large pre-trained convolutional neural networks to generate embeddings. It turns out this was not that easy because training deep models is hard. And so researchers realized that you could use skip connections to construct large networks without losing gradient flow from earlier to deeper layers. Specifically, these skip connections were designed to make sure that the model could learn, an identity function between, say, the first layer and maybe a layer near the end. Examples that come to mind and which were really driving the pack back then were things like ResNet, DenseNet, and VGG. However, post transformers, post the introduction of the Vaswani paper, we can now use transformers to generate embeddings. You might say, how does concept of words work here? Because there are no words in vision. And the answer is they use something called image patches, which sounds exactly like its description. These are the analogies of words and take into the computer vision space. Now, instead of using the output from ResNet or DenseNet, we might use a linear projection from something like VIT, which stands for Vision Transform. Okay, by the same token, let's go on to tokenization. So the other issue that we might deal with when we're setting up our NLP model is the sheer number of words. There are a large number of words, say 500,000 English, and we can't guarantee that all the words in English will be in our training set, much less all the words in the languages that our model might encounter. One particular problem in English is that words can be agglutinated, which is like arbitrarily stacked together to make new words. To make matters worse, new words are being invented every day. Think on like TikTok or Reddit. And it seems impractical to update our models every time a new word like zooted gets added to the dictionary. So how might we deal with this? What is the solution? Again, let's take a few minutes to think to ourselves and see what approaches we can come up with. We won't take the full 1 minute to think about this. So one idea is to use character embeddings. Rather than processing data at the word level, we tokenize at the character level, which means that we only ever have 26 characters to generate. However, the problem with this is that sequences can get extremely long if we're going at a character by character level. The approach usually taken these days is not in fact character embeddings, but it's sort of a sweet middle ground between characters and working with whole words. And as the slide might allude, it is subword tokenization. According to this approach, tokens be anywhere from one letter to a full word, but usually somewhere in between. Think, say, at the syllable level. A statistical algorithm called BPE, or byte pair encodings, is used to compute the best distribution over the tokens given some total token budget. I won't get too much into the details, but you can imagine this algorithm as repeatedly trying to see which pairs which sequences of letters appear most frequently. And after you compute these, you will add these really common sequences to some running total of what should be considered as a subword. Maybe a subword consists of, maybe something that we previously designated a subword plus an additional character. That way, after we apply this BPE algorithm, common words like the and can be given their own tokens, whereas uncommon words like zooted can be processed in smaller chunks. Another bonus is that models can handle similar looking words similarly. For instance, say the word think and thinking are chunked think, like maybe all 5 letters together, and for thinking, it's the first 5 together and then the next 3 together. This would mean that the model can use what it's learned about the first word to help inform how to handle the second. You can imagine this might be really helpful for other cases, right? There are a lot of synthetic adjectives in English. There are a lot of cases where we have, like, say, fast, faster, and fastest. And it would be nice if the model could treat all 3 with some sort of similarity, because they are highly correlated. So this is what we have for subwords. Another problem you might have at this point is that because we're dealing with the subwords, it's conceivable that there are multiple different ways to subword tokenize as a particular string of text. You might ask, how are you going to deal with this? And the solution that was developed is something called subword regularization. In this case, we probabilistically sample from the different ways that the subword might be split. This string might be split up during training. And we do the same thing during test time. Okay, so we just discussed attention, we discussed embeddings, we discussed tokenization. Let's move on to NLP models, putting it all together. So the real breakthrough in NLP technology came with the advent of widespread pre-training. To put it simply, pre-training involves training a model to perform some sort of self-supervised task, usually some variant of denoising, such as reconstructing missing or incorrect data, over a very large data set. Think at the size of maybe the entire internet, which is something like what Common Crawl uses. The idea is that in the process of doing this pre-training task, the model learns a lot of information about the overall distribution of language, or whatever sequence that you might be training the model on. This highly knowledgeable model can be then used as a component in a pipeline that is optimized to perform the task that you're particularly interested in. Say for text, it might be summarization, question answering, things like that. You'll hear more about this in a following lecture about transformers practice. In this section, we will briefly describe major classes of NLP models and their associated pre-training strategies that have produced large foundation models, to use the term from Stanford. In particular, we will focus on 2 major classes, encoder-only and decoder-only models. So an encoder model is one that produces an encoding, which might not be surprising to you. In particular, it yields representation for each token in the input. Decoders, on the other hand, will take some sort of representation and generate a new sequence of unbounded size. Maybe something that might be helpful is before we delve into the specifics of each, you can take a few moments to think what might each be useful for. And their use cases, I can assure you, are pretty different. So let's take a few moments and think about that now. Okay, so hopefully you've had a chance to think about this. Let's start with encoder-only models. Encoder-only models produce, actually, maybe before we get to encoder models, let's do a quick overview of the thought experiments that we just did. As it turns out, or at least according to current practices, encoder models are suitable for token level or sequence level prediction or classification tasks. Think maybe, classifying sentiment, things like that. On the other hand, decoder models are suitable for tasks where you need to generate new tokens or evaluate the likelihood of some possible new outputs. This can be conditioned on input process using encoder model. These are considered to be encoder-decoder sequence-to-sequence models, or it can be unconditional, where say GPT-3 just rambles on its own for a bit about the meaning of life. Okay, with that overview in mind, let's move on to encoder-only mass language models. An encoder-only model produces a representation for each token in the input by repeatedly iterating attention layers. After enough stages, the representation for each token is deeply contextualized with all the surrounding context, allowing one to extract information about both the tokens themselves and about the entire sequence. For this reason, encoder-only models are typically used for tasks like text classification or token classification. Perhaps a good example of a pre-trained encoder-only model is BERT. BERT is pre-trained with what is known as a mass language modeling objective, where random words in the input are replaced with a special token, say mask in all caps, or simply replaced with another word drawn at random. The overall idea is that to effectively predict which words fit in the blanks requires a wide variety of linguistic skills. Think about the fill-in-the-blank exercises that you might have done when you were in grade school, where maybe you had 4 choices, but only one of them really made sense given the context and also our knowledge of how language in the world works in general. This is precisely what BERT is learning during this mass language modeling objective. To learn longer relations between text, BERT also has a next sentence prediction task, where the model is asked to figure out whether an arbitrary sentence appears as the next sentence or not. So because of this masking, BERT and its derivatives, which you might hear a little bit more about in this lecture about transformers practice, these are referred to as mass language models, or MLMs. So maybe let's hop on to a quick demo where we try to see BERT and its mass language modeling objective in action. To do so, I will now open up a Colab notebook. Let's see if this opens up properly. So I'm going to press escape. I see we do have a question in the Q&A. And this is precisely right. I guess that was before I mentioned next sentence prediction. Thanks, Gara, for the question. Okay, so now let's open up a Colab notebook. This should be in in the notes. So you'll have access to that later. So we now have an end-to-end mass language modeling with BERT IPyNB. Hopefully you've used Jupyter before. If not, that's okay too. It's pretty self-explanatory. Let's run through one cell at a time. So first, we'll install the transformers library. We have it on quiet mode, so it doesn't spam the whole notebook with its output. And this should only take less than a minute. It won't be too long. Next, let's import the necessary libraries that we need. Transformers, NumPy, TensorFlow. We'll load something called StillBERT, which is maybe a lightweight version of BERT. You can think of it as that. So again, this shouldn't take too long. Okay, we'll now load our tokenizer, which you now know how that works. Okay, so we can imagine some sentence that this is a great something for the summer. And hopefully, if BERT has done its job right, then it will replace with summer-related words. And hopefully, they will also be nouns, because this won't make sense otherwise. Let's see how this is doing. We will run the cell, and we can say, using our knowledge of English, we can make a judgment as to whether BERT has learned the right thing or not. So we have, this is a great retrieve for the summer, this is a great spot for the summer, this is a great opportunity for the summer, this is a great place for summer, event for summer. So this all seems pretty reasonable to our human intuition. Let's try another thing. My favorite thing about the movie was Mask. Okay, let's see what this does. Popcorn, romance, sex, butterflies, Halloween. Maybe the first three seem to be a little bit more applicable than the last two. But again, it seems that the model has learned a pretty good understanding of what the word movie means, and again, how sentences are structured. So you can play around with this demo a little more. It's pretty fast to run. There are a lot of different sentences that you could try out. And this gives a pretty good feel for the BERT mass language modeling objective. Okay, so let's go back to the lecture. I'm not quite sure I understand the question. If there are different numbers of mass tokens, you can imagine that each of those tokens should be placed with the word that used to be there. So unless I'm misunderstanding something. Okay, let's go back and I'll start the slideshow again. Let's go back to our encoder models and do a quick wrap up of those. So BERT is really good at natural language understanding, or called NLU for short. If you've ever seen like maybe, clickbaity headlines that computers are, just as good as humans at reading comprehension, it was probably a BERT model. So BERT is good at drawing conclusions from existing blocks of text. But you could be open-minded. Many other tasks can be framed as token classification. Maybe a good example is question answer, which is something that Pranav himself is, pretty well known for. Just classify which tokens form the answer to your question. That said, generation is more tricky because it does not produce a proper probability distribution from which one can sample. Instead, it can probably only hint you to which words might be in the answer. To really set up a generation, it is possible. Like there is a paper for Amazon Research that does this, but what really we should be doing is using our next model type, which is decoder only models. So with that in mind, let's maybe move on to our next section about decoder-only models. So a decoder-only model consists of a transformer model that generates only one token at a time. And maybe for context, maybe it's worth mentioning on my end at least, that transformer models, the original transformer had both an encoder and a decoder. But it turned out you do not need both to achieve particular tasks. In fact, it turns out that we could get equally good, if not better results by only using the encoders or only using the decoders for specific aims, which we're outlining right now. So back to decoders. A decoder-only model generates only one token at a time. To do so, the model is trained to, or given some leftwards context, to predict the next token. You can see this GIF that's being animated right now. Thanks, Jay Alomar, for this GIF. Basically, it's quoting a line from Asimov, "A robot may not." And you can see that it's predicting the tokens one word at a time, given the previous context. In this case, the context is partially shaped by the model itself. It's just going with the most likely token and tacking it on to the existing context to the left to make a sentence. By repeatedly iterating this process, a transformer decoder can generate extremely large extracts of realistic seeming text. Maybe a good example is the GPT-3. You might have heard about this in the news, maybe like a year or two ago, about maybe a year ago, about stories that seemed almost as if they were written by a human. Or let's face it, sometimes they're better than human. So a good example is GPT. These models are trained to, as we said, generate the next word given some context to the left. This simple objective allows for the generation of extremely realistic text. In addition, by providing information about the task that you would like the model to solve in the left context, maybe you can say, oh, summarize this, or maybe you can say, rephrase this. One can produce extremely capable emergent behavior. This is referred to as prompting. What are some decoding methods that these models use? They might include beam search, top K, and top P sampling. Because of this leftward context that we've outlined, GPT-X, GPT-2 or GPT-3, and its derivatives are referred to as left to right language models, autoregressive language models, or maybe sometimes simply language models, not to be confused with the mass language models that we learned about in the previous section about encoder-only models. So now you know the difference between MLMs and LMs. Just as we did a demo for BERT, I think it's time to do a demo for our GPT and its related models. To do so, I'll open up another Colab notebook, which is again available in the hyperlinked section in the notes. So I'm going to press escape. So this notebook requires change the runtime type to GPU. So let's do that right now. Let's change the hardware accelerator to GPU. And let's save that. This notebook is adapted from Aaron Akbulut. So let's run the cells. We're going to install TensorFlow as last time. So let's see what happens. This will take a little bit of time, but it should not be terribly intensive. Okay, so we've installed that. let's git clone OpenAI, which developed GPT-2s. Let's git clone their repository. Okay, let's cd into GPT-2. Now let's install the requirements and the required dependencies that this model will need. Okay, let's download the model. This will take about 30 seconds. Okay, let's cd into GPT-2 again. Oh, okay, oh wait, I already did this. This is a mistake. Let's delete this part. Now let's pip install Colab extern. This is just going to give us a fake, terminal environment, or like iTerm if you use that, in which we can run the model. So let's cd into GPT-2. We're already there. Now let's run the interactive conditional samples.py. Sounds like there's some bug going on. That's odd. I literally checked this demo like earlier today and it was working. I'm not entirely sure what's up. In any case, maybe I can debug this offline and make sure it's just ready for the notes that you can check back to later. Basically, the idea was that we were going to be able to, type in some context and the model could continue. That's really weird though. Let me look at this for a second. I don't understand why this is not working. That's a little weird. Okay, maybe in the interest of time, let's not worry about this for now. So I will fix this for future reference. I'm not entirely sure what's going wrong here, but it just seems like maybe we have a dependency issue or something. So we won't worry about this for the time being right now, unfortunately. That's a shame. Okay, so let's go back to the slideshow. One important point when using a generative model is the sampling strategy. As I referred to earlier, technically one can randomly sample a token from the probability distribution at each step. However, this kind of approach can often fail due to incorrectly calibrated probabilities, which is a hallmark of neural language models. There's a lot of work on calibration, at least at Stanford. There are several methods to alleviate this, such as beam search, top P sampling, temperature, and top K sampling. In effect, all of these aim to find a good balance between high likelihood generations and relatively varied generations to make sure we have a nice variety and interesting mix. The exact balance is usually a function of the exact task that you're trying to solve. Decoder-based models are extremely good at generating new spans of text. For this reason, they are often used for generative tasks such as writing, dialogue systems, and story generation. One can also condition the decoder section of the model on a separate encoder. These are called encoder-decoder models and are an example of sequence-to-sequence models. Encoder-decoder models solve a wide variety of tasks, including transferring from one kind of information to another, like machine translation. speech recognition, image captioning, and typo correction. However, when you're trying to figure out which model to use, which is probably something that you will do in the future, it's important to understand the major considerations. For example, a multiple choice question might seem to naturally solved by an encoder-only model like BERT, then classifying the resulting sentence embedding using a K-way classifier. However, it is also possible to frame it as a sequence-to-sequence problem, where one tries to generate the answer as plain text. Similarly, any sequence-to-sequence problem can also be reframed as a decoder-only problem by putting that input in the left context of the model. It's also important to remember that a decoder is required to generate a proper probability distribution, thanks to its left to right characteristic. While decoding, models are obviously not able to look at tokens that they have not yet generated. There are masks for this if you look at the code in some of these decoder models. By contrast, masked language models are typically able to see all the text in both directions. Maybe you can think about it as, being able to see through the back of your head or something. So they are not able to generate a proper probability distribution, although there are ways to get around that, as I mentioned previously. Finally, remember that decoder models are O of number of decoder steps. So an inefficient framing of the problem requires significant copying of tokens. This might cause extreme waste of resources. So these are maybe some of the considerations to keep in mind as you decide which class of models to use. Maybe another thing worth mentioning is BART, which is a sequence-to-sequence denoising model during the pre-training objective. It involves deleting, masking, rotating, and infilling different words in the input sequence, which the decoder then reconstructs. BART is often used for summarization, among other things. Okay, I think that's all we have lined up. So in summary, today, this last hour, we learned about a couple different things. We started with an understanding of the fundamentals behind transformers. Things like attention, things like embeddings, things like tokenization. Then we moved on to, to compare and contrast these, mass language models and language models, and learning a bit about what you might use each for, and maybe the characteristics that make them applicable and highly useful for different settings. Hopefully, after this lecture, you'll have a bit more insight into the theory behind transformers.
Great. Thanks a lot, Ryan, for the wonderful lecture covering all of these aspects that are very critical for a lot of work that's going on now. So thank you for covering that. There are a couple of questions in the Q&A if you want to take a look at those.
Sounds good to me. Thanks, Gaurav. Thanks for the thanks. In LLM, each sentence with one mask given as a single sample for train, if I am correct in my understanding. Yeah, that seems right to me. I'm not entirely sure what the question is. So if you want to clarify that, I can also look at that. Are there cases in which an MLM might predict multiple words to take the place of the masked word? Rather than multiple possibilities, it would predict a pair of words instead of one spot in place of the mask. Is a perfect spot versus this is a perfect vacation home for the summer. You're saying, would it predict multiple words? There are ways to do that. Like if you look at the infilling paper, maybe I think it's called Teaching Language Models to Fill in the Blanks by Chris Donahue. I think you can see how they are able to infill with multiple words. I don't believe that BERT does this, but it is certainly possible. And it's also pretty interesting because the good thing about doing something like that is that you can now have, pretty good control over whether you want to infill with something long or something short in the BERT style. Or maybe like, if you have something long, maybe you want to insert a whole new sentence, something like that. But that's also pretty interesting to think about. Yeah, sounds good. I believe that's all the question. Could you please post a link to that paper? Yeah, for sure, I can do that. Language models. Okay. Really find the ACL. Okay. Type answer. Cool.
Awesome. Wonderful. And thanks again, once again, Ryan. This was really wonderful, and thank you for sharing the session with us.
Thanks, Prana, for having me.
Great. I'm gonna hit pause recording here.